Hi dears, today we can see CSIR NET related problems. So the first question is, how many elements does the set Z belongs to C? Z power 60 is equal to minus 1, Z power k not equal to minus 1 for 0 less than k less than 60 have. The question here is, how many elements does the set have? So we have the result. Set S is equal to Z belongs to C, Z power n equal to 1, Z power k not equal to 1 for 0 less than k less than n, then cardinality of S is equal to phi of n. So we can relate this with this question. So Z belongs to C. Here Z power n equal to 1 we need to get. So here it is minus 1. So make this as 1. So for that squaring on both sides, Z power 60 the whole square, which gives 1, and Z power k is also not equal to 1 for 0 less than k less than, because between these two values k will be present, that will be never be 1. Okay, it may be minus 1. So 0 less than k less than 120 means 60 into 2, which is 120. So Z power 120 equal to 1, Z power k not equal to 1 for 0 less than k less than 120. So the cardinality of S is equal to phi of n. So phi of n is phi 120. We have to find phi 120. So we know that phi 120, Euler-Torsion function, you have to use it. Okay, Euler-Torsion function means phi of n. That is the number of positive divisors less than n and which is relative prime to n. That is torsion function, Euler-Torsion function. So you can write 120 as this form, that is 2 cube into 3 into 5. So all are prime. So pi 2 cube into pi of 3 into pi of 5. So pi of 2 cube, you can use this one. Pi of Pn is equal to, that is P is prime. So P power n minus P power n minus 1. Use this one, you will get this. That pi of 3, which is 2, because pi of prime number is equal to P minus 1. So 3 minus 1 and 5 minus 1, 2. So you are getting, that is 32. So option C is the right one. Let's see the second question. Let C be the counterclockwise oriented circle of a radius 1 by 2 and centered at I. Then the value of contour integral over C dz divided by Z power 4 minus 1 is. So here C is the circle with a radius and centered at I. So this is the form. Modulus Z minus I is equal to 1 by 2. Center is I and radius is 1 by 2. So first your denominator is equal to 0. So Z square plus 1 and Z square minus 1 equal to 0. So that you will get 4 values like plus or minus I and plus or minus 1. So we can find this one by using Cauchy residue theorem or Cauchy integral theorem. So I am using here Cauchy integral theorem. That is f of z naught is equal to 1 divided by 2 pi I integral over C fz divided by z minus z naught into dz. So out of these 4 values, which will be the correct fit, this one we have to see. So we have mod z minus I is equal to 1 by 2 and we have 4 values. Z is equal to I. Substitute here, which is 0. 0 is less than 1 by 2. Again Z is equal to minus I, which is here minus I minus 2I. So modulus of minus 2I, that is 2. Modulus of I, which is equal to 1. So greater than 1 by 2. So this gets fails. Then Z is equal to 1. Substitute here 1 minus I, which is equal to root of, this is 1 square plus the coefficient of I is minus 1. So minus 1 the whole square, which is root 2, which is greater than 1 by 2. So this get fails. Then Z is equal to minus 1. The same category we have to do, so that this is greater than 1 by 2. So the only one pole is Z is equal to I. That fits this criteria. So that we can substitute this one. So we have to find f of I is equal to 1 divided by 2 pi I integral over C. What is Z naught here? I. So we have to write like this, integral over C. Fz value is 1 divided by these values. Z plus I, then Z plus 1, then Z minus 1. Z minus 1. The only one is, okay, you can see this one. Fz is this value. This Z is equal to I should be come at the denominator. So this is the Fz value. Okay, this is Fz value divided by Z minus Z naught. So let's see how to find this integral. Yeah, Fz is equal to this one. So we have Z is equal to I, that is the pole. So Z f of I is equal to 1 divided by 2i, I plus 1, then I minus 1. So 1 divided by 2i, I square minus 1. That gives minus 4i, right? So we have to find this one, integral over C Fz divided by Z minus Z naught into dz, we have to find it. So which is equal to 2 pi I into f of I, that is Cauchy integral theorem. Cauchy's integral theorem. So 2 pi I into f of I is 1 minus 1 divided by 4i, cancel, minus pi by 2. So option D is the right one. Option D is the right. Next question. This is just like entrance questions. Number of positive divisors of 240. Okay, the question here is number of positive divisors of 240. So 240, that n can be written as, any number can be written as p1 power r1, p2 power r2, etc. pk power rk. So number of positive divisors, the formula is r1 plus 1, r2 plus 2, plus 1, etc. rk plus 1. So this 240 can be prime factorized like this. So 2 power 4 into 3 power 1 into 5 power 1. So this is R1, R2 and R3. So plus 1, 5, 1 plus 1, 2, then 1 plus 1, 2. So by calculate, we will get the number of positive divisors of 240 is 20. So before we see an Euler-Tauschen function, right? So that is pi of n. That means number of positive integers less than n that are relatively prime to n. That is Euler's Tauschen function. So here pi of 11 is equal to 10. So you have to see positive integers less than n. That means number of positive divisors less than 11 and relatively prime to 11, you have to take it. So you have to see GCD of the number 1, 11 which is equal to 1, or 2, 11 you can take, that is equal to 1. That is no other common factors except 1. So 3, 11 which is equal to 4, 11, etc. etc. Such a type, if you see, you can see 10 numbers we will get like that. Okay. So pi of 11 is equal to 10. Otherwise, we have a result that if p is prime, then pi of p is equal to p minus 1. So here 11 is a prime number. So 11 minus 1 which is equal to 10. Right. Next example. The last we see that pi of 8. So that you can write as 2 cube. Right. So also we have one formula, pi of n is equal to, you can write n into 1 minus 1 by p1 into 1 minus 1 by p2, Euler product formula, etc. 1 minus 1 divided by pk. Okay, pk. So here you can see that a prime number can be written as p1 power r1, p2 power r2, any number can be written as, okay, etc. pk power rk means you can write this one. So 8 you can write as p power r or p1 power r1. No other is there. So 2 cube. So use this formula. What you are getting? 8 into 1 minus, here p is what? 1 by 2. So do this, which is equal to 4. Or you can use another one formula, this formula, or the other formula you can write pi of p. If it is a prime number, you can write that as p power n minus p power n minus 1. Okay. Pi power n. Pi power n you can write as p power n minus p power n minus 1. So here you can see 8 which is 2 cube, right? So 2 cube minus 2 power 3 minus 1. So 2 square. So which is equal to 4. So any formula you can use for this Euler-Tauschen function. Okay. So 3 formula we learned here. Pi of p which is equal to p minus 1 if p is prime. Okay. The second one you learned this one, pi of n is equal to n into 1 minus 1 by p1, 1 minus p2, etc. 1 minus pk if p is not prime. Like that. So p1 power r1, p2 power r2, etc. pk power rk. Again you can see that pi of n is equal to p power n minus p power n minus 1. This also we can see. Okay. Let's see the next question. This is CSIR NET 2012 question. Okay. Let f be a entire function if imaginary of f is greater than or equal to 0, then real f is constant, f equal to 0, f dash is non-zero constant. So it is an entire function. Let's take this function f is equal to e power iz, which is an entire function. Put z is equal to x plus iy, so e power ix minus y. Take modulus on both sides, so e power ix into e power minus y. So this is cos x plus I sin y. Here we have imaginary of f is greater than or equal to 0. So 1 into e power minus y. So this is 1 divided by e power y. So by carrying all the values, this will be less than or equal to 1. So we can say modulus value which is less than or equal to 1 gives f is bounded function. Already in the question we have f is entire function. Now we have bounded. So entire plus bounded gives a constant function. That is Liouville's theorem. If f is entire and bounded, then f is constant. Liouville's theorem. So you can see that option B and option A is right, because option B is f is a constant. Just now we found by using Liouville's theorem f is constant, and f is constant means you can write that real value of f is also a constant. We have the result. If f is a constant, then real value and the imaginary value is constant. So such a way here A and B is true. Let's see the third one. Third option, f of z is equal to e power iz. E power iz. So e power iz, that value is never be equal to 0. Okay. Because we have imaginary f is greater than or equal to 0. From that itself you can see that e power iz is not equal to 0. But in the option C given f is equal to 0. So option C is the wrong one. And option D, it is given that f dash is a non-constant, non-zero constant. That is given in the question. Okay, option D is f dash is non-zero constant. Here you can see f is equal to C. Okay, f is equal to C. F is a constant. So whose differentiation is equal to 0. So what it is given here, non-zero. But here we got as 0. So option D is wrong. So for this problem, option A and B is the correct option. Let's see the fourth one. Let f z be a non-constant entire function and z is equal to x plus iy. Then let u xy, v xy denotes its real and imaginary part. Which of the following is false statement? The question here is non-constant entire function. We have a result that a non-constant entire function satisfies the CR equation. Okay, entire analytic function which satisfies the CR equation. So CR equation is ux is equal to vy and uy equal to minus vx. This is from part B question, right? So we can see the first option is right. Ux is equal to vy and uy equal to minus vx. But the question here is false. Here it is opposite. Uy equal to vx. This is the wrong option. False, right? So according to this question, answer B is the right one. Similarly, you can find C and D. So for that, f of z is equal to u plus iv, that you have to take that u plus iv. Then you have to differentiate with respect to x, means f dash is equal to what? You will get that as u x plus I vx, right? Then you can use the CR equation to change this one so that you will get this option. Or you can take the squaring on both sides, f dash the whole square, which is equal to what we will get, a root of, right? You will get like this, a root of ux square plus vx square the whole square, so that you will get the C option. Similarly, you can see with respect to y, we will get the D option. So according to this question, the false statement is B. Let's see the next question. Let omega not equal to 1 be an nth root of unity. Show that 1 plus 2 omega plus 3 omega square etc. plus n omega power n minus 1 is equal to. 4 option is given. So let's try for third root of unity, fourth root of unity, fifth root of unity, so on. So just I am took here fourth root of unity, so that Z is equal to fourth root of unity. That is, unity means 1 power 1 by 4. So that you can write, return in the polar form as cos 0 plus I sin 0 the whole power 1 by 4. That is 2k pi plus I sin 2k pi the whole power 1 by 4, where k carries the value 0, 1, 2, 3. So divided by 4 and cancelling, you will get k pi by 2 plus I sin k pi by 2 for k equal to 0, 1, 2, 3. Let's take the values here. K is equal to 0. Substitute here k equal to 0. So cos 0, 1 plus sin 0, 0. So that it is 1. K equal to 1, you will get cos pi by 2 plus I sin pi by 2. So sin pi by 2, 1, cos pi by 2, 0. Then I into 1. Now k equal to 2 means 2 and 2 get cancelled. Cos pi plus I sin pi, that is 0. So here it is minus 1. Similarly, k equal to 3. Okay, so we have 4 roots. N equal to 4, so we have 4 roots. Now I am not taking this value because in the question it is given omega not equal to 1. So the 3 roots are I, minus I and minus 1. Let's stick with this 3 options. Okay, so omega is equal to I. I am taking the first one, omega equal to I. So while substituting this in the option wise, n divided by omega minus 1. So I tried for here fourth root of unity. So n is equal to 4. Now I took omega. The root here is what? I. So I minus 1, which you can substitute in the question. 1 plus 2i plus 3i square. Then here 4i power, 4 minus 1, that is 3. Okay, so that you can see here 1 plus 2i plus 3 into minus 1 plus 4 into I cube, that is minus I. So that here you can see that 1 minus 3 minus 2, then this minus 2y. We have to equate these two. If it's so, we can say this is the roots. Okay. So 4 divided by I minus 1 is equal to minus 2 into 1 plus I. We can take the conjugate. So that minus 2 a plus ib into a minus ib is a square plus b square divided by 1 minus I. So minus 4 divided by 1 minus I. Then here the denominator we have to change as I minus 1. So take minus outside. So you can say that 1 divided by I minus 1. So n divided by omega minus 1 is the true option. Okay. So here n divided by omega minus 1. If you need that, you can try with the remaining also to satisfy this condition. The question here is to show that. See here, the question is show that. Okay. Thank you.